Just as mass is the intrinsic property that creates gravity, electric charge is the intrinsic property responsible for electromagnetic forces. It comes in two types: positive protons and negative electrons. Opposite charges pull together, while identical charges push apart. Because charge is a scalar quantity measured in coulombs, it has magnitude but no directional vector. That brings us to your first core property for Class 12, additivity. Finding the total charge of a system is simply basic arithmetic. If we define this jar as our system and drop in a +2 charge, a +4 charge, and a -5 charge, we add them up algebraically. 2 + 4 - 5 leaves a net system charge of exactly +1 coulomb. Any macroscopic charge you encounter is simply the final arithmetic tally of the individual discrete particles contained within a specific boundary. Moving from static math to physical processes introduces the second property, the conservation of charge. When you generate everyday static electricity by rubbing a balloon on your hair, you are not creating a new charge out of thin air. Zoom in on that friction, and you will see a mechanical transfer. The positive protons remain locked tight within their atomic structures. Only the negative electrons are scraped off the hair and transferred onto the balloon surface. The math here is strictly zero-sum. The hair becomes positively charged because it lost electrons, and the balloon becomes equally negative because it gained them. But within this isolated system, the total net charge remains perfectly constant. A localized charge is never a completely new creation. It is only a temporary imbalance borrowed from its surrounding environment. This formula layout illustrates the third key property, quantization. Q represents the total charge, N is any whole integer, and E is the elementary charge constant, the exact charge of a single electron or proton, valued at 1.6 × 10 to the -19th coulombs. Charge is quantized because it can only scale in discrete, whole steps. You can transfer 1 electron or 1,000,000 electrons, but you physically cannot transfer half an electron. Let's lock this in with an exam-style calculation. If a neutral glass rod loses exactly 5,000,000 electrons, what is its final total charge? Pause the video here, run the numbers, and watch your signs. Step 1 is direct substitution into the quantization formula. We map our whole integer, 5,000,000, to n, and multiply it by our elementary constant, E. The math yields 8 × 10 to the -13th coulombs. But the crucial step is assigning the positive sign. Because the rod lost negative electrons, it leaves behind a net positive charge. Every electrical measurement ever recorded, no matter how massive, is simply an integer multiple of that one fundamental constant. Charge and mass have distinct dynamics. First, dependency. Mass exists independently of charge, like a neutral neutron, but charge requires a mass anchor. Second, invariance. At relativistic speeds, mass fluctuates, but electric charge remains rigidly locked at the exact same value. Charge is an absolute value, an invariant property tethered to matter, regardless of how fast that matter is moving. This is your Class 12 cheat sheet. Grab a screenshot. The 4 pillars. Additivity proves charge is an algebraic sum. Conservation shows it's transferred, never destroyed. Quantization restricts charge to whole numbers of E, and invariance proves it ignores velocity. Mastering these 4 properties provides the strict mathematical foundation you will need for every electromagnetism equation going forward.